of the future HPC technology in wind energy modeling and simulation. Today's session highlight is on HPC performance computing for wind resource assessment. Today we will have 3 talks and a final quick note from our project coordinator. So let me first introduce our first speaker, Jake Badger from DTU, Technical University of Denmark. Jake received his BSc at Imperial College London and PhD in meteorology at Reading University in 1997, where he completed also his postdoc in 2000. He is a head of section for resource assessment modeling and in DTU and responsible for management of nearly 20 scientific working modeling in wind condition for regional to site states. He has 20 years
Mohsen, you muted.
I'm so sorry. I'm so sorry.
But you had, I think you got most of the introduction through. So
yeah, I sorry. I thought. Okay.
Yeah.
From where I was muted.
Yeah, I think you were nearly finished. It was about the section. Yeah.
Okay. So let me cut it there and let's welcome Jake Badger. Please start with your.
Yes.
One question. Are you happy for us to record your?
Yes, that's fine. Yes.
Thank you very much.
Yeah. Okay. Thanks, Mohsen. Before
you start, please everybody who's not speaking and turn off your camera and speakers so we can have focus on the Jake presentation. And after the presentation, please use the chat or raise hand or just unmute yourself and ask your questions. Thank you very much.
Thanks, Mohsen. So I'll go ahead. Thanks everybody for joining again. So this is a presentation by me and with materials from my colleagues Dalibor Carver and Bjarke Olsen, all of us at DTU Wind Energy. And it's of course at this conference, and I want to highlight how this project, HPCWE, has allowed us to make some developments within the mesoscale to microscale model chain for wind resource assessment, and to strike a note on the importance of HPC in case we were in doubt about that. So go to the next slide. So the first of all is the motivation. So I would say the big motivator for us at DTU Wind Energy is to be able to produce more accurate wind resource assessment. And why does it matter so much? If you do sort of a back of the envelope calculation and you say, well, what would be the impact of a 1% error on a wind resource estimate? If you look at the cost of energy, which is around $75 per megawatt hour, if you look at the IEA estimate from 2020, this is like a mean between offshore and onshore wind energy. And then if you have a 100 megawatt wind farm with a 35% capacity factor, which is quite modest these days, I would say, there could be much more, it can be more than that. But a 1% error in the annual energy production, this AEP, is approximately worth $230,000 per year. So a 1% error there is quite significant, and maybe the errors are more like 5% or 10% in more complicated situations. And then we have, if we look at how many wind farms are installed per year, so we're looking around 50 gigawatts of installed capacity per year globally. And so if you think about the 1% error there and its value, it's about $100 million per year. And this is an effect that, of course, will accumulate during the lifetime of a project. So why do we need to care so much about it? It's because, well, a positive bias can lead to performance below expectation. So your estimate might have been over-optimistic. But a negative bias can lead to unrealized projects. So that if an estimate, if a resource map was showing the resource poorer than it was in reality, it might have actually stopped projects happening that could have been very successful. And then a random error that is affecting these estimates can lead to a greater uncertainty, which is a low P90 here, which is an exceedance value, which is sort of giving you a worst case scenario estimate. But if that value is low and there's a higher uncertainty, that can lead to higher capital costs of a project, which again may mean that it doesn't happen or makes the cost of energy more expensive. So hopefully these are good reasons to feel motivated to do something about making more accurate wind resource assessment. When I describe the work we're doing in this section, the wind resource assessment modeling section at DTU Wind Energy, I usually show this slide because it shows a model chain going from this, which is the globe on the left, where we can see over many decades we can get data sets like the ERA data set from the European Centre for Medium Range Weather Forecasting, which has a state of the atmosphere for many decades over the entire globe, but at a resolution that's not sufficient for wind resource assessment, but still very useful for giving us long-term state of the atmosphere conditions. So what we need to do is this downscaling, this arrow, where the first step after going from the reanalysis data is to this mesoscale modeling. Here we see Mexico and the Gulf of Mexico, and actually a hurricane in development moving across here, this red area is high wind speeds. So this is the regional with the mesoscale modeling. And then this isn't high enough resolution to do an accurate wind resource assessment. For that, you need to know about the hilltops and the lake sides and the coastline and so on, roughness changes. So we need to go to the site level, which is at the end of this downscaling. Here we can use very fast linearized flow models, for example, in WASP and PyWASP, as we have developed at DTU Wind Energy. So we can actually start to get estimates of turbines placed on hilltops. Or we can also use LES modeling to tell us something about the variability on scales and timescales relevant to wind turbines. So I can actually press that animation. This is from Berg et al. From 2015. So this is a whole model chain for downscaling, and it requires a lot of high performance computing. So if you look at the ECMWF, I was just on their webpage looking at their system. They have this Cray XC40 system, which can give them around 8,500 teraflops, which is nearly 1% of exascale. I thought it was interesting to see that in terms of exascale. And obviously this is something that is, they also do forecasts, and its meteorology is a very big user of high performance computing. And then locally, if looking at our own system here at DTU Wind Energy, we have access to the Sophia cluster, which has around a theoretical maximum of around 300 teraflops. So we're still way off the exascale, but you can see we are needing these kind of machines to do our assessment. And the important thing about what I want to say about wind resource assessment and our modeling is that we do kind of rely on models that are, say, used by for other purposes. So the reanalysis data has a whole lot of different users and stakeholders who want to get that reanalysis data. The WRF mesoscale model is also a model used by many different users for weather forecasting, for research, and then there's also a community using it for wind resource assessment. So it's important to say that we are users of these models, but it's important how we use them in the best possible way for our purpose. And that sometimes means we need to do things that are sort of making them more custom made to our purpose. And it's there where we need to think about the HPC aspects as well as the physics aspects behind our changes and modifications to the codes. So a nice way to frame all of this wind resource assessment is to look at the Global Wind Atlas as an example. DTU first launched this in 2015, but we're now actually on our third version, and we have as partners Vortex, who is also a partner on this project, and Marta spoke before the break from Vortex. So we're happy to work with them on this project. And we also had some financial support from the World Bank Group and SMAP. But what I want to say about this project and this sort of product, the Global Wind Atlas, is that it is also demanding a great deal of computer resources. So we have mesoscale modeling using WRF simulations, so the resolution for the whole globe, or the land cover, and 200 kilometers offshore was 3 kilometers. So we're actually looking at just the horizontal grid alone with 10 million points. And then you also have the vertical levels on that, raising it by an order of magnitude or a bit more. And then we have simulations done for 10 years. So this is around 10 million time steps of mesoscale modeling once you've added it all up. And that's Vortex were responsible for that part of the Global Wind Atlas. And then if you look at the microscale modeling part, which is using the DTU model WASP, linearized flow modeling, we did that with a 250 meter grid spacing. So horizontal grid total alone there for the whole of this coverage was 1.5 billion points or thereabouts. Again, we have multiple heights, so raising it by an order of magnitude, but it just is indicating the scale of these kinds of calculations and the computer resources needed to do that. So this is a nice map, but of course we know it's got challenges, and some of the main challenges are about the uncertainties and how to correct or get better or reduce those uncertainties. So there are two main aspects that are increasing the uncertainty here. One is the complex terrain areas. So, and this is approximately about 10% of the world's surface is what we would classify as complex, where the linearized flow models aren't performing so well. And within the project HPCWE, we have a test case called test case number 2, which is in Pedregao, which is it's a complex site, and we will be using our model chain alongside partner model chains to make improvements to our physics modeling and also the HPC aspects. And then the other part, which is challenging, is offshore areas, which are huge areas with huge resources, but fewer in situ measurements. So whereas on land it's easier to put up an anemometer for a few years and get a resource estimate on, for offshore it's not so straightforward. It's very expensive, or you may be using remote sensing methods instead. So, and in fact that's test case 3, and that's in collaboration with our Brazilian partner in this project, the Federal University of Santa Catarina. So this is wrapping up those challenges within what we have in this project. And I would just like to say, so this is actually zooming in on the coastline of Santa Catarina, where you see even like an offshore area. If you can see my mouse on the bottom right-hand side here, this color going from red to yellow is the mean wind speed, going from around 10 meters per second to sort of around 6 or lower in this coastal area. So it's just offshore, it's still ocean surface, but there's still a variation which is important to model correctly if the wind farm is going to be able to produce and perform as we would like it to. So even offshore, things are quite complex. So it's good we have that test case in this project. So to talk, sort of zoom in more closely now with the DTU wind energy model chain, one of the areas we've been concentrating on is this chain going from the WRF mesoscale model to the ellipsis 3D CFD model, which has been developed at DTU Wind Energy. And there's a method which is using tendencies from the WRF model to force to drive the CFD code. This was written up in San Rodrigo et al. In 2017, and Bjarke Olsen, who is on this project at DTU Wind Energy, has used it as part of his PhD study, and now is being developed further, and that's what I will explain here. So it uses body forces to drive the CFD code, and it uses time and height dependent, this is the original setting, time and height dependent forcing. So you're forcing columns. So if we look at this side, we have a forcing which is based on a tendency from the advection term, so bringing momentum into a grid. And then we also have this term, which is the pressure gradient force, also creating an acceleration. So we can get these terms from the mesoscale model and then use those to drive the CFD codes. So what we have here is the description of the grids in the microscale model and the grid in the mesoscale model. And there's also an equation for the temperature as well. And then these forcings are made, or this tendency update is made every 10 minutes from the WRF model into the, so we get information from the WRF tendencies every 10 minutes. So what is new in the 2020 project through this project? What is new in 2020, the year 2020 in this project? We have two parts. We have a new way of averaging of the physics tendencies from the WRF model, and we have a new way of applying the tendency fields from WRF into ellipsis 3D. And both parts, we need to consider what that means for the physics and how we want to improve the accuracy of the wind resource assessment, and what it means in terms of the high performance computing aspects. What does it mean in terms of the performance? So the first one is related to the inline averaging of the physics tendencies. So pre this project, the tendencies averaging was done as post-processing. So every 5 seconds from the WRF modeling, for each time step of the WRF modeling, tendencies were written out by the WRF model. And now inside this project, it's been possible to implement the method of Cheng et al. 2020 into WRF, when this allows the tendency averaging performed during the execution, which is what is called the inline averaging, and improves the pressure gradient tendency term, which contains a lot of high frequency signals that are not of actual significance or don't have an impact on the larger sort of resource needed. It's just sort of noise that is not helpful for us. So what does that meant? So if you look at the WRF setup for the Pedagao case, we have this nested domains going into higher and higher resolution and zooming in on the area of interest. So this is carried out as normal. But what we have now at a domain, this is actually around 1 kilometer domain, we're taking out this gradient term. So this is the pressure gradient force for the U tendency. So this is how the wind speeds in the east to west direction or west to east direction are influenced by pressure gradient. And if you get that out in the old way, which was these instantaneous pressure gradient information, it contained a lot of noise. In the middle plot, you see the inline averaging method. And this is looking at a horizontal slice at 100 meters, and you can see the difference is quite significant. And then we can also see this in terms of a vertical slice through the Pedagao site again. So in the old method, there was a lot of noise in that instantaneous version. So and then the inline averaging is giving this much sort of cleaner picture, where it's mainly the signal left that's important. So in these ones, you can see these features. If you look at the middle there, you can see some red and blue where there are tendencies that are causing acceleration in the U, in the X direction, that you want to capture in the CFD. Whereas in the instantaneous version, there's a lot of noise that is of no consequence to the general flow, because in the next time step, it will be maybe even another sign. Okay, so and if we look at the comparison of using the post-processing averaging and the inline averaging, you can see that the two methods are agreeing. So we're not losing any fidelity in doing this inline averaging compared to the sort of heavy post-processing averaging. If we take the frequency every 5 seconds, if we take the pressure gradients every 5 seconds. And you can see the blue line here is showing the amount of variation there is as we go from time step to time step. And this is important. So if you're doing a post-processing method, you really would need to be doing a lot of I/O. You would be having to write out every time step in order to get an accurate picture of what is the pressure gradient term. So this is what this graph is showing you, that after 2 days, the mean absolute error as a fraction of the mean magnitude of the pressure gradient is growing quite significantly. So even if you only wrote out every 2 minutes, this would give a mean absolute error of around 20%. So this is a big advantage for us in this methodology, to be able to do the inline averaging. So tests from a 2-day simulation with the old and the new method for Pedagao case on one node with 32 cores. Pre this project, it would take 256 minutes and produce 3.2 terabytes of data. But within this project, it's now 73 minutes and 109 gigabytes of data instead. So the new method has reduced the time. So we've multiplied the time by 1/4. So we're using 1/4 of the time, and we're producing 1/30th of the amount of data. So this is a big saving when using this method. We can free up a lot of resources. So those freed up resources have several implications. How can we use those? Well, we can increase the mesoscale modeling resolution, for example. We can increase the simulation period, or we could set up mesoscale multi-model ensemble runs to test the range of realizations that you can get inside a mesoscale modeling setup. So these are sort of trade-offs that we make, but freeing up these resources allows us to see how we could enhance other aspects of the modeling. So part 2 is about new 3D tendency fields from WRF. So if you remember before, as a reminder from slide 7, that these tendencies were height and time dependent only. And then I've just talked about this averaging of the PGF, the pressure gradient forcing. But now actually it's been made, Dalibor has been working on making it so that it's no longer a 1D horizontally averaged column that is affecting the whole ellipsis 3D simulations. So pre-HPCWE, we would look at a location and find out how does the pressure gradient change in time. So in these graphs, we're going from 12 o'clock to 12 o'clock the next day. And you can see the height here,
right.
How the pressure gradient is changing with time. But remember, it's a single column changing. And then we have the advection term here, which is also showing you how this is what is occurring for the single column, which is used to force the ellipsis code. But if we go to the new part, so what in HPCWE has been possible is that the tendencies information from WRF is now 3D, and now you can think of it as many columns of tendencies for covering the ellipsis 3D domain appropriately, and still they evolve in time. So the mesoscale tendencies from one vertical profile would look like this if it was covering a 27 by 27 kilometer ellipsis area of interest. Now we can go to doing it with these 3 by 3 kilometer profiles. So we end up with 81 profiles now instead of 1. And if we look at that, Dalibor has done this for the Cabal case as a sort of proof of concept. So we look at the wind speeds from the WRF model and the wind speeds that are coming out of the ellipsis 3D codes as evolving with time. So we got the same going from 12 o'clock one day through to 12 o'clock the next day for 3 different days. And you can see that there's an evolution of the wind speed through the day. So during the night, there's this low-level nocturnal jet feature coming about, which is quite challenging to model. And we can see that we can get it in the mesoscale model, and we want to also to get it in the microscale model ellipsis 3D. And you can see that we can get that here, and we can actually preserve more of the features of that nocturnal low-level jet by using this 9 by 9, the 81 profiles, to do the forcing of the ellipsis codes. Then we can go up another level, and now this is the 1 by 1 kilometer profiles. So we have 27 by 27 profiles, so it's now 729 profiles, and we can see the same again. So now this is showing you with the 1 profile, and you can see in this case by the 3rd day things are going astray with in this proof of concept when we don't do the multiple columns. We just have 1 column representing a 1 by 1 kilometer from the mesoscale. If we do this now with the 729 profiles covering the 27 by 27 grid, we get a much better representation of the evolution of the wind speeds through these days. So this is now kind of demonstrated for a more simple flat case. But the concept is that now we can extend that to more complicated cases like Pedregal, for example. And that's been done. So Dalibor has done that with numerous ways of doing this multiple column approach. And you can see we've got all of these results now, and we can compare it with the measurements from the Pedregal case. And the Pedregal case had a very intensive measurement period where we have a lot of data, And now we're actually at the point where we need to see which of these setups was best. What is the best way of forcing the ellipsis 3D with the information from the mesoscale model? It could be that if you take too high, if you take 1 kilometer profiles, for example, that is actually too high resolution, and you may be sort of forcing the model to be more like the mesoscale model, whereas maybe there's something at a sort of in between that. Maybe the 5 kilometer or 9 kilometer would be the right place to be doing the forcing. But that's something we need to find out still within this project. So we can evaluate for the different sites the time series, the average profiles as shown here for the different setups, also the windrows. And I say that particularly because for this location, there's an anemometer in the valley here, which is very difficult to capture, that the flow is actually running aligned with the valley, even when we have winds in the larger scale, which are going more either southwesterly or northeasterly. So you can see that in this windrows here, the black line is showing what the measurements are. And then these different colors are showing you what the ellipsis 3D results are given these different kinds of setups. So somewhat the ones that are looking better are these these ones where you allow for more profile information, but maybe not too much. So this is still something to be found out and concluded on, I would say, at this stage. So the summary from this part 2 is that the proof of concept of using 3D mesoscale tendencies from the 29, the 9, and the 3 and the 1 kilometer domains has been implemented and executed for 3 sites, including the Pedregal site. Choosing the best configuration with validation cases is still underway. The implementation of the method for integrating mesoscale forcing of various complexity, going from scalars to 4D fields, is now part of the ellipsis 3D code. So it's in the generic data stream now, so it's possible for any users of ellipsis to do it that way. And the IO operations in ellipsis, when using these time-varying 3D mesoscale tendencies, have been identified as something that could be improved to reduce the IO bottlenecks, because now we think with this level of input going into ellipsis that this will be something that will slow down it could be done faster. And that ends my presentation. Thank you for your attention. It's my email if you want to send me a question by email or make contact. Thank you.
Thank you very much, Jake. Very nice presentation, very informative. I'd like to ask the audience if anybody have any question, please use the raise hand option, or if you don't have access to that one, just unmute yourself, or you can, if you're shy, you can use the messaging. While we're waiting for if anybody has any question. Okay, let me, I have a couple of questions. I have 2 questions actually for you. How is your approach for the validation of this mesoscale, microscale approach? That's one question. Mm-hmm. And the other one is on slide 4, you show the globe and the data from collected over several years. I presume that it's more than like 20, 30 years, something like that. And I'm wondering how would be accurate using those data with these global warming and changing on everything that it's ongoing now?
Good questions. So the first one is related to the validation, and that's an important part of this project, in that we have actually 3 test cases, and 2 of them are touching on this wind resource assessment part. Case 2 is the Pedregal site, where we'll be doing modeling also alongside partners Vortex and EDF in this project. We'll be using their methods, and we'll be comparing with our methods for getting improved. So our benchmark will be the results from the new European Wind Atlas for Pedregal, and then we'll be aiming, so we have key performance indicator, which is an incremental improvement on the actual accuracy of our method compared to the baseline from the new European Wind Atlas. So that's one of the places we'll do the validation using this intensive period, as I mentioned, this intensive measurement period. And then the other validation will be done in case 3, which is off the Santa Catarina coastline in Brazil, where there's a measurement being made by the university there, the federal university there, where there's a LiDAR being positioned and also sea surface temperature measurements. So we'll be running the mesoscale modeling and microscale downscale there, comparing against the LiDAR profile. And there the emphasis will be on, from our side, will be mainly on looking at the mesoscale simulations, how to capture sort of the range of realizations there by doing multi-model mesoscale simulations, whereas in Pedagao, the emphasis will be more on the downscaling at the microscale part, where we'll probably have more effort on the microscale modeling and use different ways of clustering to get statistical representation of the conditions. And then about the, unless you want to jump to another question, about the reanalysis data. Yeah, the whole, one of the main purposes of the reanalysis data is to have a kind of single approach, a single model to data assimilate all of the measurements that have been made around the world for the last few decades into a system where, because it is a single model, any change or trend in temperature can be identified as being part of the change of nature rather than due to a change of the model. So it is right that although we have a sort of model consistency throughout that period, so we would expect to identify changes in that have come about due to climate change. But there are still differences in the amount of measurements that have gone into those, like the amount of satellite data that's there is increased vastly in the last decades compared to when you go back to 3 or 4 decades ago.
Thank you very much. We have a question from Peter Taylor. Could you explain ellipsis 3D versus high resolution nesting?
Yes. So I'll try that. So what we have with ellipsis is a resolution down to meters scale, whereas at the WRF modeling with the nesting there, we would go down to, well, it depends. You could go down to 9 to 3 to 1 or even to 333 meters, if you like. It's a question of where do you want to pass the mesoscale modeling information to the microscale, to the ellipsis. So could you explain ellipsis 3D versus high resolution nesting? So I wouldn't say they're necessarily versus. It's more like you want to do the WRF modeling with some nesting down to a certain point and then pass that information, say the tendency information, to the microscale model, which would be at the high resolution. The reason why that it can get complicated is there can be an overlap. So you may have, in Pedagao, for example, there are these 2 ridges that are parallel to each other. It might be that you could double count, you risk double counting those if you go to high resolution in the mesoscale and then go to high resolution in ellipsis. So we're wondering if it's better to sort of stop with the mesoscale before you resolve those ridges and then only introduce the ridges at the microscale.
Okay, thank you. Apparently there's not any more question. Thank you very much, Jake, for a nice presentation. Okay, let's go for the next.